Rain and man. Rain and man. We have to find the relative velocity of rain with respect to the man. Rain and man. We have to find relative velocity of rain with respect to the man. With respect to the man. Rain and man. Rain and man, relative velocity of the rain with respect to the man. In the diagram, this is a man which is moving towards east with a velocity vector vm. A man is walking east. A man is walking east with a velocity vector vr. So this is the direction along which the man is walking, and in the diagram it is shown that the man is walking with a velocity vector vm east. That means vector vm is the velocity of the man, and the man is moving east and the opposite side is west, and the rain falls vertically downwards with the velocity vector vr. In this case, the rain falls vertically downwards with the velocity vector vr. So along this direction, that means rain falls vertically downwards with the velocity vector vr. In this case, the rain falls vertically downwards and the man is walking east with the velocity vector vm. Here the man is moving east. The man is moving east with the velocity vector vm. Man is moving towards right, and rain falls vertically downwards. With the velocity vr. Rain falls vertically downwards with the velocity vector vr, or with the velocity vector vr. Now the relative velocity of rain with respect to the man is vector vrm is equal vector vr minus vector vm. That is, vector vrm is the vector difference between the velocity vector vr and vector vm. Vector vrm is equal vector vr minus vector vm, which is the relative velocity of rain with respect to the man. Vector vrm is equal vector vr minus vector vm. So therefore, vector vrm can be written as vector vr plus under bracket minus vector vm. Vector vrm is equal vector vr plus under bracket minus vector vm. That is the relative velocity of rain with respect to man. Vector vrm is equal to vector vr plus under bracket minus vector vm. Vector vr, in this case, vector vr should be added with minus vector vm. To find vector vrm, or to find the relative velocity of rain with respect to man, here vector vr will be added with minus vector vm. That means velocity vector vrm. To find vector vrm, obviously to find vector vrm we have to use parallelogram law. And if we draw a parallelogram, whose two adjacent sides are represented by vector a and vector b. Here vector a and vector b are represented in magnitude and direction by two adjacent sides OP and OQ of the parallelogram. Vector a and vector b are represented by two adjacent sides OP and OQ, and this diagonal will be the resultant vector. That is parallelogram law of vector addition, and vector r is equal to vector a plus vector b, which is the resultant vector of vector a and vector b. Now vector vm, that is velocity of the man vector, is acting away from the common point O, and vector vr is acting towards the common point, and here vector vm is acting away and vector vr is acting towards the head, towards the man. That is, vector vr is acting towards the common point o, or velocity of the rain. That is, here the height of the man is the common point o, and vector vm is acting away from the common point o, or and vector vr is acting towards the common point o. To find vector vrm, which is vector vr plus under bracket minus vector vm, velocity of the rain should be extended in the forward direction, and vector vm is acting towards right, and vector vm is extended in the opposite direction. That means equal and opposite velocity of the man should be imposed on the velocity of the man, so that the man comes at rest, and the man will observe the motion of the rain. In this case, we can draw a parallelogram or rectangle to apply parallelogram law. That means to get the resultant velocity vector vrm, which is equal to vector vr and minus vector vm. So to find vector vrm, or to apply parallelogram law, we can draw a rectangle that is a parallelogram. That is a parallelogram such that velocity of the rain, that is vector vr and minus vector vm are represented in magnitude and direction by the two adjacent sides of this parallelogram or of this rectangle. And in this case, according to law of parallelogram or parallelogram law of vector addition along this diagonal, the resultant velocity, that is vector vrm, which is the resultant of vector vr and minus vector vm, will be acting along this diagonal. Vector vrm is the relative velocity of the rain with respect to man, which will be acting along this diagonal, Therefore, vrm is the relative velocity. vrm, vector vrm or vrm is the relative velocity of rain with respect to the man. Relative velocity of rain with respect to the man. And this relative velocity vrm acts along this diagonal. Hence, we can say that the rain, though the rain is falling vertically downwards, but the rain will appear to fall from this direction. The rain will appear to fall or appear to come from this direction with the relative velocity vector vrm. Vector vrm. This is the direction along which the rain will appear to fall. The rain will appear to fall from this direction. From this direction, rain will appear to fall from this direction with the relative velocity vrm at an angle phi subtended by the vertical direction. Phi is the angle subtended by vrm with the vertical direction. With the vertical direction. Therefore, we can say that the man should hold his umbrella at an angle phi east of vertical to protect himself from the rain. Therefore, the man has to hold his umbrella. The man has to hold his umbrella in forward direction at an angle phi east of vertical. The man should hold his umbrella in this way to protect himself from the rain. This is the umbrella. This is the umbrella which will be uh, in the forward direction at an angle phi with the vertical. This is the umbrella, and the man has to hold his umbrella in this way at an angle phi east of vertical. The rain will appear to come or fall from this direction with the relative velocity vector vrm, and to protect himself, the man has to hold his umbrella at an angle phi east of vertical. Here we can write in the diagram that man has to hold his umbrella at an angle phi east of vertical, at an angle phi east of vertical. Again, we can explain in what way rain will appear to fall with the relative velocity Vr. Here, the man is walking east with the velocity Vm, and rain falls vertically downwards with the velocity Vr. And we have denoted east and west direction. Man is walking east, and rain falls vertically downwards. Here, rain falls vertically downwards with the velocity Vr. Let Vm be the Vm be the velocity of a man. Vm be the velocity of the man of a man walking east. Vm be the velocity of man walking east. That is along. That is along OA. Vm be the velocity of the man walking east. That is along OA, and the rain falls vertically downwards. The rain falls vertically downwards. The rain falls vertically downwards with a velocity Vr. With a velocity Vr vertically downwards. That is along YA. That is along YA. The relative velocity of rain with respect to the man. The relative velocity of rain with respect to the man. The relative velocity of rain with respect to the man. The relative velocity of rain with respect to the man is vector vrm is equal vector vr minus vector vm. Vector vr plus vector vm, or here what we can write, vector vrm is equal vector vr under bracket minus vector vm. That's why we can write vector vrm as equal vector vr plus under bracket minus vector vm. That is the relative velocity of the rain with respect to the man. Vector vrm equal vector vr plus under bracket minus vm. So here this is equation 1, that is the relative velocity of rain with respect to the man, which is equal to vector vr plus under bracket minus vector vm, under bracket minus vector vm. Therefore, minus Vm is added with vector Vr to get the relative velocity, that is vector Vrm. Vector Vrm. Therefore, minus vector Vm is imposed on vector Vr to find vector Vrm, that is to obtain the relative velocity of rain with respect to the man. Minus vector vm is added, that means minus vector vm is imposed on vector vr to find the relative velocity of rain with respect to the man, that means to find vector vrm. And again minus vector vm, that means equal and opposite velocity of the man, that is minus vector vm is imposed on the velocity of the man, that is minus vector vm is imposed on vector vm to bring the man at rest so that he can observe the rain will appear to fall with a relative velocity vector vrm. That is, minus vector vm is imposed on vector vm, that means added with vector vm to bring the man at rest so that the man observes, that the rain appears to fall. The rain appears to fall. The rain appears to falls with a relative velocity, vector vrm, with a relative velocity vector vrm. Therefore, therefore, equal equal and opposite velocity of the man, that is minus vector vm, equal and opposite velocity of the man, that is minus vector vm has to be imposed on has to be imposed on the velocity of the man, that is on vector vm, to bring the man at rest, to bring the man at rest and also minus vector vm means equal and opposite velocity of the man, that is minus vector vm has to be imposed on the velocity of the rain, that is on vector vr, so that the man brought to rest, observes the rain, so that the man brought to rest observes the rain which will appear to fall with a relative velocity vector vrm, vector vrm. Therefore, equal and opposite velocity of the man, that is minus vector vm, has to be imposed on the velocity of the man, that is on vector vm, to bring the man at rest. Also, minus vector vm has to be imposed on the velocity of the rain, that is vector vr, so that the man brought to rest observes the rain which will appear to fall with relative velocity vector vrn. Now we can draw a rectangle or parallelogram to find the apparent velocity or relative velocity of rain with respect to the man. This is the parallelogram, and minus vector Vm and vector Vr are represented in magnitude and direction by the two adjacent sides of this parallelogram. And here this parallelogram is drawn to find the relative velocity of the rain with respect to the man. According to parallelogram law of vector addition between the two vectors vector Vr and minus vector Vm, along this diagonal vector Vrm will be acting. Along this diagonal vector Vrm will be acting. That is the relative velocity of the rain with respect to man. That means vector Vrm will be acting along the diagonal of this parallelogram. That means here vector vrm is the relative velocity of rain with respect to the man. Angle between vector vm and vector vr is theta, which is equal 90 degree. Theta is equal 90 degree, which is the angle between vector vm and vector vr. Now we can represent the angle between vector vr and minus vector vm. We can represent the angle between vector Vr and minus vector Vm. That should be 180 degree minus theta. According to parallelogram law of vector addition, Now we can make a correction, that is vector vrm, vector v small rm should be written as vector v capital Rm. That means relative velocity of rain with respect to the man should be denoted by vector v capital R small m. So this relative velocity of rain with respect to man should be denoted by vector v capital R small m. Vector v capital R small m. Now according to parallelogram law of vector addition, mod vector vrm is equal root over mod vector vr square plus mod minus vector vm square plus 2 mod vector vr into mod minus vector vm cos 180 degree minus theta, cos 180 degree minus theta. So here theta is the angle between vector vm and vector vr, and angle between vector vr and minus vector vm is this angle, which is 180 degree minus theta. 180 degree minus theta is the angle between vector vr and minus vector vm, angle between vector vr and minus vector vm, and this angle 180 degree minus theta is used in the expression of mod vector vrm, or comma vrm equal root over vr square plus vm square plus 2 vr vm cos 180 degree minus theta, cos 180 degree minus theta, where mod minus vector vm is equal to vm only. Mod minus vector vm is equal to vm, or comma vrm is equal root over vr square plus vm square minus 2 vm cos theta. vrm equal to root over vr square plus vm square minus 2 vm cos theta, where cos 180 degree minus theta equal minus cos theta. vrm is equal to root over vr square plus vm square minus 2 vm cos theta, or comma vrm equal to root over square root vr square plus vm square minus 2 vm cos 90 degree, where theta, that is the angle between vector vm and vector vr, is 90 degree. Theta is equal to 90 degree. In the diagram, rain falls vertically downwards with the velocity vector vr, and man is walking east with the velocity vector vm. That's why angle between vector vr and vector vm is this angle, that is theta equal 90 degree. Theta is equal 90 degree, as vector vm is perpendicular to vector vr. The man is walking in the horizontal direction and rain falls vertically downwards. That's why theta equal 90 degree. Therefore, vrm equal root over vr square plus vm square. vrm is equal root over vr square plus vm square. That is the relative velocity of rain with respect to the man, provided rain falls vertically downwards with the velocity vr, and man is walking in the horizontal direction with the velocity vm east. So vrm equal square root vr square plus vm square. That is the relative velocity of rain with respect to here the man. In the diagram, rain falls vertically downwards with the velocity vector vr. Man is walking east with the velocity vector vm, and rain will appear to fall from this direction with the velocity vrm, such that vrm is equal to root over vr square plus vm square. It should be v capital rm, and relative velocity of rain should be denoted by v capital rm. Now we can denote the angle phi, which is the angle subtended by the relative velocity of rain with respect to man. That means phi is the angle subtended by vrm with the vertical direction. Here phi is the angle. Phi is the angle subtended by the relative velocity vrm with the vertical direction. Here the direction of vrm is measured at an angle phi with respect to the vertical direction. Let phi be the angle with which phi be the angle with which the rain will appear to fall, appear to fall with the relative velocity Vrm with the vertical direction. Let phi be the angle with which the rain will appear to fall with the vertical direction. With the vertical. So in the diagram, obviously due to relative motion between the rain and the man, the rain will appear to come from this direction with the relative velocity vector Vrm. And that means rain from this direction, appears to fall from this direction at an angle phi east of vertical. That means phi is the angle subtended by vector Vrm with the vertical direction. Therefore, tan phi is equal mod minus vector Vm sine 180 degree minus theta divided by mod vector Vr plus mod minus vector Vm cos 180 degree minus theta. Cos 180 degree minus theta. In the diagram, phi is the angle subtended by vector Vrm with vector Vr. That's why vector Vr is the first vector, and other vector means minus vector Vm is the second vector. And we have to explain the expression of tan phi. Now we can draw a parallelogram. Two vectors, vector A and vector B, are represented in magnitude and directions by the two adjacent sides of a parallelogram, and this diagonal is the resultant vector. And two vectors act at an angle theta with each other. Vector R is the resultant vector which makes an angle phi with vector A. That's why vector A is the first vector, and other vector, that is vector V, is the second vector. Vector V is the second vector. And here tan phi will be equal to magnitude of second vector sine angle between the two vectors, that is sine theta, divided by magnitude of first vector plus magnitude of second vector cos theta. That is the expression of tan phi. Now we can use this concept for the two vectors, vector Vr and minus vector Vm. Now vector Vr and minus vector Vm are represented by this parallelogram or rectangle, and we are drawing the diagram again. And this is vector Vrm, that is the relative velocity of rain with respect to the man. The angle between vector Vr and minus vector Vm is 180 degree minus theta. Vector Vrm makes an angle phi with vector Vr. Now vector Vr is the first vector, and minus vector Vm is the second vector. And magnitude of second vector means magnitude of minus vector Vm is used here. That means second vector minus vector Vm is the second vector, and first vector means vector Vr comes at this position, and again minus vector Vm comes in the denominator. An angle between vector Vr and minus vector Vm, that is 180 degree minus theta, will be with sine function and cos function in the denominator. Or tan phi is equal Vm sine 180 degree minus theta divided by Vr plus Vm cos 180 degree minus theta, where mod minus vector Vm is equal to Vm. Or therefore tan phi is equal to Vm sine theta divided by Vr minus Vm cos theta. Tan phi is equal Vm sine theta divided by Vr minus Vm cos theta, where cos 180 degree minus theta is equal to minus cos theta. Cos 180 degree minus theta is equal to minus cos theta, equal Vm divided by Vr, since theta equal 90 degree. Therefore tan phi is equal Vm by Vr. tan phi is equal to Vm by Vr. That is, tan phi is equal to velocity of man divided by velocity of rain. Therefore, phi equal tan inverse Vm by Vr. Phi equal tan inverse Vm by Vr, where phi is the angle subtended by vector Vrm with vector Vr. Therefore, phi is equal tan inverse. Phi is equal tan inverse velocity of man divided by velocity of rain. Phi is equal tan inverse velocity of man divided by velocity of rain. Therefore, when a man is walking east in a horizontal plane with a velocity vector Vm in rain, with a velocity vector Vm in rain, which falls vertically downwards with the velocity vector Vr, which falls vertically downwards with a velocity vector Vr, with a velocity vector Vr, comma, then the rain appears to fall with a velocity Vrm, equals square root Vr square plus Vm square. The rain will appear to fall with a relative velocity Vrm equal root over Vr square plus Vm square. Vrm equal root over Vr square plus Vm square from a direction, from a direction or from the forward direction at an angle phi equal tan inverse Vm by Vr. Phi equal tan inverse velocity of man divided by velocity of rain east of vertical. Hence, the rain will appear to fall with a velocity Vrm equal root over Vr square plus Vm square from the forward direction at an angle phi equal tan inverse Vm by Vr east of vertical. When a man is walking east with a velocity vector Vm in rain, which falls vertically downwards with a velocity vector Vr, the rain will appear to fall with a velocity Vrm equal to root over Vr square plus Vm square from the forward direction at an angle of phi equal tan inverse Vm by Vr east of vertical. The rain will appear to fall with a velocity Vrm from the forward direction at an angle phi east of vertical. So in the diagram, the man has to hold his umbrella in the forward direction at an angle phi east of vertical to protect himself from the rain. In this case, phi is the angle subtended by the umbrella with the vertical direction, and that means the man has to hold his umbrella at an angle phi east of vertical in the forward direction. Also, here again we can say that also the man should hold his umbrella at the same angle. The man should hold his umbrella at the same angle. At the same angle, the man should hold his umbrella at the same angle of phi equal tan inverse Vm by Vr east of vertical. The man should hold his umbrella at the same angle of phi equal tan inverse Vm by Vr east of vertical in the forward direction to protect himself from the rain, to protect himself from the rain,